This video is about piecewise functions. If you take a look at your definitions and theorems page, you'll see the definition of a piecewise function is a function in which more than one formula is used to define the output of different pieces of the domain. So in layman's terms, what we have is multiple functions in one function, so pieces of functions that are broken up along the domain of the graph. Okay, so for example, let's say I had a straight line, x plus 5, but only if the graph is before the negative 2. So I'll do a real quick sketch. So what I'm doing here at negative 2 is saying this function is different than this function. And then the second function, x squared plus 2x plus 3, if x is greater than or equal to negative 2. So starting at negative 2 to the right-hand side, I have a quadratic function. Now we could graph these on the graph, but when I did that with my in-person students, it confused them. So we'll look at the graphs of them in a few minutes. But what we're going to focus on is evaluating a function. So we've done this already, but now we're going to evaluate it when I have two different options. What you're going to do, sorry, I have the hiccups, is this is x. So we're going to compare this x to our domain. So we're asking ourselves, is 3 less than negative 2, or is 3 greater than or equal to negative 2? Well, on my little sketch over here, 3 is over here, so we're going to use the second equation to evaluate f of 3. So I'm going to plug in 3 to this equation right here, which gives me 3 squared plus 2 times 3 plus 3, that is 9 plus 6 plus 3, which is 9 plus 9, which is 18. So I input a 3. I had to figure out which equation I input it into, and then my output is my answer. Notice that I put in a number, and my output is a number. So there's a point on the graph at 3, 8, 18. That's what I just found out. So 3 at 18, there is a point on the graph. Okay, now I can also evaluate at a different number. So I can give you another problem. So this time, negative 4, we're going to do the same method. Is negative 4 less than negative 2, or is negative 4 greater than or equal to negative 2? So on my number line over here, negative 4 is here. So we're going to use the first equation because it's on the left-hand side where the first equation exists. So negative 4 goes in place of my x, and then I have negative 4 plus 5, which is 1. So there is a point on the graph at negative 4, 1. So here we have a point on the graph. What I'm looking for, your answers, is the one that I have boxed. You can also write it as a point if you would like. What happens if we have a negative 2? So here's where you have to be able to read the inequality symbol. This one has an equal to line, so negative 2 can be equal to negative 2 in only this equation. Because this one is not equal to, there's a hole on the graph here, so it doesn't exist in the first equation, but it does exist in the second equation. So we just input a negative 2 into the second equation. So we have 4 minus 4 plus 3. So the answer is 3. So there is a point on the graph at negative 2, 3, even if it's not on the other part of the graph. If you know how to do it, you got it. Go ahead and try your homework problems. Problems 1 and 2 1 through 3 actually on your homework. Sorry. If you need another example, I'm going to do another example. Okay. In this example, let's say f of x is negative 2x plus 1 if x is less than or equal to 2, but if x is greater than 2, then it is the absolute value of 5x minus 4. Okay, for this problem, I want you to find f of negative 4. Okay, so we're asking ourselves what's happening on the graph is at 2, we're changing direction. So I'm going to split my graph here so I can see it. Negative 4 is all the way over here before 2. So I want to use the graph that is less than 2, which is this one right here. So negative 2 times negative 4 plus 1 gives me 8 plus 1, which is 9. So there's a point on the graph at negative 4, 9. Now I want to try one that is in the absolute value function so I can answer how do I do it if it has an absolute value, because I believe there's one on your homework. So 8 is bigger than 2. It falls over here on our number line. So we want to use this equation that says it's bigger than 2. So we have the absolute value of 5 times 8 minus 4. When you have that, sorry, just a second. Okay, some issues pop up with the absolute value because when we solved for it, we set it up for 2 equations. But that was because our x was unknown. When you have an x that is known, you just solve the equation like normal inside and then make sure when you take your answer out of the absolute value that it's positive. So let me show you what I'm talking about. This is 40 minus 4. 40 minus 4 is the absolute value of 36. Because this is a positive number, there's no change. If that would have been a negative 36, when I took it out of the absolute value, it would still be a positive 36. So just be careful with that on your homework. So we just found out that at 8, our graph exists at 36. Okay, so now that I've shown you how to do this, I didn't want to draw any graphs because I didn't want to confuse you. But we can work on your homework together. So if you look here at, I don't know, let's do number 5. Your version is probably better than mine because I've copied a copy here. So I'm hoping that you can see this graph better than I can. But what we're going to do here is find all of these x values and decide what their y value is on the graph. So at negative 1, we're going to go to x equals negative 1 on the graph. Here it is, right here. Well, it just so happens to be that our graph passes through negative 1. So the point on the graph here is negative 1, 0. So the answer that I'm looking for is 0. Okay? At x equals 2 is here. So I'm going to go until I have a point on my graph. And there's one, this line is connected. You can't see mine very well. Here you go. There's one here at positive 1. So this point is 2, positive 1. So the answer that I'm looking for is 1 because here's the 2, here's the 1. Same thing with this one, negative 1, 0, negative 1, 0, 2, 1. Just a point on the graph. Let me do one more for you. At f equals 1, ooh, yeah, I need to do this one. At 1, so here is x equals 1. If you notice, I have 2 points on my graph. This happens sometimes. The difference in my points here is one of the points is a filled in point. You see how it's an actual point? It's colored in. The other one is an open circle. This open circle is not included. It will never be the answer because the point doesn't exist here. This point is the point that's the answer. Because it's a shaded in point, it's included as part of this graph. So at 1, we have a point at 1. So 1, 1. Not 1, 2, but 1, 1 is our point. So this answer is 1. So that's how you do the graphs. So you have 3 of them to complete. This one is very easy. It's just at -2 what's happening. So be careful here. You're going to go all the way up. Okay? At -2, go all the way up to the graph. You should have lines. You can tell that my lines are gone, so it's a little more difficult. Okay, now I'm going to show you how to do the backside of your homework. We have a bunch of what are called polynomials. So we need to take a look at our definitions and theorems page. I'm on the very last page, page 3, to see the behavior of polynomials. I'm going to move to page 2 for just a second so we can take a look at the definition of polynomials. So a polynomial is a smooth, continuous graph. It can be a curve, it can be a quadratic, it can be a quartic, it can be whatever we want it to be. It just means multiple terms. This is the formal definition for a polynomial. So these are all possible terms, and if you look, the powers decrease, right? We're going to use this information to help us in a few minutes, but what we're going to do for this assignment is look at the intervals of increasing and decreasing. We're going to look at the extrema, which means max and min, and we're going to look at the inflection points on the graph. So all of these definitions are what we're talking about in this part of the video right now. So for me, what I found important is that an increasing graph happens when we have a positive slope on the graph. Now keep in mind, we're going to read our graph left to right, just like we're reading these definitions. So that means a decreasing interval is going to have a negative slope on the graph. You can find that slope or that rate of change using the same method that we used when we did linear functions. We're not going to focus too much on the average rate of change, but you can find it by finding the changes in the x's and the changes in the y's. We're going to look at 2 different types of minimums and maximums, a relative and an absolute. Sometimes I'll say local. Oh, it's right here. Sometimes I'll say local when I say relative instead of relative. They mean the same thing. And then we'll talk about a point of inflection. One thing that's not on these is concavity. So we need to add this to your definitions and theorems page, please. A concavity is talking about the shape of the polynomial graph. So I've drawn some pictures so you can kind of see what's going on. In this picture, you'll see that we have a minimum point. This is a concave up graph. And I remember it because it looks like a cup. It can hold water in our graph. If our graph is turned the other direction, and it makes like a hill or a frown, you see how I made a frowny face? That's because it's concave down. It will have a maximum point. Where we change concavity, if we go from concave down to concave up, where we've started to change concavity, this is called a point of inflection. That's where we're changing. It makes kind of like a cubic area. If you think of a cube function, oh, well, that's a terrible cube function, but it has a concavity change. The same thing happens from concave up to concave down. Now, one more thing before you can get started. We have 2 different types of symmetry. You can have a function that's symmetrical across the y-axis. So, for example, let's say we have this function. Mine's not perfect, but it's pretty close. It's an even function, and it's lined up on the y-axis so that it has what I'm going to call even symmetry, or you can say it's y-axis symmetry. There's a line through the middle of the graph where the left side is equal to the right side. So that's y-axis symmetry. But odd symmetry is going to be origin symmetry. That's usually found in odd degreed functions. So for example, a cubic function is an odd degree function. It's not the same on the left and the right. If we fold it in half, this side will be over here and this side will be over here. But it is the same if I rotate the graph, and now the function looks the same even though I flipped it over. That's because it has origin or rotational symmetry. So I'll ask these on your graph. Some of them have even symmetry, some of them have origin symmetry, but if your graph isn't lined up, let's say I put this one on a graph, this graph has neither, because when I rotate it, it's not odd symmetry, and when I fold it, it's not y-axis symmetry. Okay, so let me take a look at a graph here. I'm just going to draw a random graph, but I do want to make sure that your endpoints are smaller than our min and max, just so we can make a point here. So it doesn't have to be exactly like mine, but it needs to be generally like mine so it makes sense. So what I'm saying is, notice that this hill is higher than this point. This point is lower than this, is not lower than this hill. Okay, so here we have a couple of things. Now I used endpoints instead of arrows for a very specific reason. That's because given an arrow here and an arrow here, we won't have absolute maximums or absolute minimums. So just keep that in mind. But right now, this is the highest point on the graph. It's the topmost point, so this is called an absolute maximum. This one is the lowest point on the graph. No other point is as low as this one. So this is our absolute minimum. So these are two extrema. Sorry, I got to talking and I spelled minimum wrong. I-M-U-M? I don't know. It looks fine. So this is the very top of the graph, and this is the very bottom of the graph. Now, there are other peaks and valleys inside those points. They are relatively tall compared to the other area, are relatively low compared to its other area. That's why we call them relative maximums. They're not the highest point, but they are high around their other points. And then relative minimums Now keep in mind, instead of relative, I could have used local, and that's another kind of visual word to help you remember that it is kind of tall locally, but if I look at the entire picture, it's not the tallest point. Okay, so that's the difference between absolute and relative. Now what we're going to look at is intervals of increasing and decreasing. Once you mark your relative mins and relative maximums, it's easier to see your intervals of increasing and decreasing. One way to do this is to think of it as a little roller coaster. So, sorry, I'm loud. I'm going to get a little roller coaster. Here's my little roller coaster. We're going to go along the graph with our roller coaster, and we're going to think about our movement. So as I'm moving along this graph, I'm moving downwards. And then I change at my turning point here. I start to turn and I go back up. And then I change again and I go back down. And then I turn again and I change and I go back up. And then I turn again and I go back down. So sometimes you'll hear these mins and max, instead of the word extrema, you'll hear turning point because of this idea. So what we've just found is that our graph is decreasing first, and then it increases, and then it's decreasing again, and then it's increasing again, and then finally it's decreasing. So we can use the x values at these minimums and maximums to write an interval of decreasing, and then we write a u for this space, and then another interval for decreasing, and then a u for this space, and then another interval for decreasing. It's not as easy to do it without points, so I'll move in just a minute to points, but we'll have two increasing intervals. So we'll have an increasing interval here, a union for this space, and then an increasing interval here. And now these x values should be repeated here and here, and then here and here and here and here and here and here, right? We share x values. If that doesn't make any sense right now, it will in just a few minutes. So be patient with me. One more thing I want to mark on the graph is our points of inflection. Sorry, I forgot to write our intervals. Just a second, let me add that on here. If you don't like the method of using like a roller coaster, you can use an arrow. So if I made this into an arrow, it would point down because we read from left to right, right? If I made this into an arrow, it points up. That tells you increasing. Down, up, down. So you can use arrows to show you increasing and decreasing also. Okay, points of inflection. Points of inflection are halfway between a minimum and a maximum. So you could find the average of those points, and that would be your point of inflection. I believe on your homework I made it easy enough for you to kind of estimate those points of inflection. That's fine with me. So here we have a minimum and a maximum. Halfway between the 2 points is a point of inflection. We have a minimum and a maximum. Halfway between the 2 points is a point of inflection. Notice that I don't have any here because we don't actually know where the turning point is on this last 2 sections. Okay, let's put it to work. I can link this page if you would like. Maybe I'll remember. But I just want you to be able to see a couple of problems. So I printed out a few problems for you to see using numbers. Okay, so in this first graph, this is a cubic function. It's odd. It's almost symmetrical, but it's not. So I would say if this was here in the middle, it would be symmetrical. But as far as symmetry, I would put neither for this symmetry. And if you've already looked at your homework, you know that that spot exists on your homework. Okay, so here is a relative max, and I'm going to put the point this time because I want to use the point to find my intervals, and this point is at -2, 1. So relative max at -2, 1. And we have a relative min at, let's call it 1, -1.5. If I had multiple relative mins, I would just list them with a comma. Or multiple relative max, you could just list it with a comma. The only time that you need the u is if you're doing an increasing or decreasing interval. Okay, so let's look at our intervals here. Where is my graph increasing? Well, we're going to assume that these are arrows, so this is infinity, until this first point. And then it starts to decrease, and then it turns again, and it's increasing from this point and then to infinity. So we have an interval. We start at the beginning, negative infinity, and then it stops at this point, -2. And then there's another interval, so I need a u for union. And we start again at this turn at 1, and then we go on to the graph forever, so negative infinity. Notice that I used parentheses for all of them. You use parentheses because this point is not increasing and it's not decreasing. It is an extrema, so we need to not include it in our interval. For our decreasing interval, there's only 1 in this graph, so we don't need a union, but the decreasing should have the same x values from here, and I'll check and make sure it does, a -2 and 1. So the decreasing interval is in between this interval here. It fits in very nicely where that u is. Okay, now we have a point of inflection that we need to label, a POI. Point of inflection is halfway between these 2 points. Because they're on a graph, we can like mathematically do that. It's at somewhere here, right? I mean, we can graphically do that. We can see where the point of inflection is. If we want to be precise, we can do the math by averaging out these 2 points. So -2 plus 1 over 2, that's the average, adding it together and dividing by 2. It tells us that it is at -0.5. And then if you wanted to find the real point, if you had an equation, you could plug it back in. We're going to kind of guesstimate it. It looks like it's -0.5 and -0.5. Okay. Let's do another one, and then I'll let you try your homework. I want to try this one because it's got a lot of intervals. So where is it increasing? Well, before I can do my intervals here, I need to find my extrema, my min and my max. So I'm going to go through and label all of these points. Notice that I don't have any absolutes. So if I had absolute available, I would just put none. So if something doesn't exist, just put none. These are all relative, and I know that because of the arrows on the end. So this is a relative max, and the point is, oh goodness, I'm going to kind of guess here, it's about -524. Then we have a relative min at -4 on the y-axis, but -2 on the x-axis. So -2, -4. Another relative min, max. Wow, I'm struggling today, sorry. At least I got rid of my hiccups, though. And that one's at -1.8. And then another relative min, and this guy, -44 on the y-axis. Sorry, the x-axis, and +2. Oh my goodness, I'm backwards today. +2 on the x-axis and -44 on the y-axis. I apologize. Okay. So, where is it increasing? It starts off increasing. So we say from -infinity to -5, and then we need a union. Oh, we cannot read that. There we go. Because it's going to increase again right here in this little spot. It's a little tiny increase, but it does increase, so we have to note it. Starting at -2 and ending at the -1. Then we have another one, so we need another union here because it's increasing at the end, starting from 2, ending at infinity. And then our decreasing graph is the points in between. So you can use those points on your information that you've written down, or you can grab them from the graph. We have a decreasing starting at -5 all the way until this minimum at -2. It turns and starts to increase, and then it turns again at -1 and decreases down until it gets here at +2. So that's our increasing and decreasing intervals. For the point of inflection, there's multiple points of inflection. I'm going to try to see if I can find them. It's probably here. So that is -3.5 and 12. And then we have more. We have another one. Oh gosh. 1, 2, 3. I'm going to call it here at negative 1.5. It should be halfway between the 2 and the negative 1. So it's negative 1.5. And then halfway between 8 and negative 4. Oh, gosh. Is that 4? Okay, and then the last one is in between these two. So at 1 somewhere, we're just going to guesstimate 120. Okay, so that is actually all your homework. I think I only put it in one video this time. So you have one video, you have 10 problems. This should be an easy week, especially with last week's difficult. It wasn't difficult, but there was a lot of information in last week. So this week is a breeze. Next week you have off, take a little break. If you want to go ahead and do homework 9 and be a week ahead, you can do that as well. I'll make a video for that in just a second and I'll post it for you. If you have any questions, go ahead and reach out to me. And keep in mind that I chose harder problems for the notes than the problems that are on your paper. So it should be a little bit easier on your paper.